Alright, well here we are again for part 2. This is lesson 34, and we're calling this double integration deflection part 1. Part 2 will be tomorrow. Now, I have a few lesson objectives here, or learning objectives. First of all, I should mention that we are in sections 12.1 through 12.2 of the Hibbler text. And my objectives here are again to explain the relationship between elastic bending moment and deflections at any point in a beam. Well, we already looked over that, we already did the derivation. But then, given a simple loading on a beam, derive an expression for beam deflections at any point on a beam. And 3, identify the boundary conditions on a beam and use them to solve for a constant of integration. So basically, just like we did when we were finding shear and bending moment diagrams, we wanted to be able to develop the or we needed boundary conditions if we wanted to do an integration. And we'll need to do the exact same thing here. We have an integration, we have an integral, and we're always going to need some number of boundary conditions therein. Alright, so I am essentially, or what I'm basically going to do is, I am going to draw first I'm going to list the tools that we developed last time, the formulas for our deflection and such, and then I'm going to work through a single long form example. Alright, so the tools here. What tools do we have? Tools. By tools, I just mean the equations that we got from the previous derivation. And these, of course, well, we have our familiar ones from statics. V as a function of x is equal to the integral of negative w of x dx. M as a function of x is equal to the integral of v as a function of x dx. So moment is the integral of shear. Shear is the negative integral of load. The slope of the beam, theta of x, is equal to the integral of m as a function of x over ei dx. And y as a function of x is a special one, that's the double integral, m as a function of x over ei dx dx, or we can think of this as equal to the integral of theta as a function of x dx. And for this, the same sort of rules would apply. If you have discontinuities, you're going to need to break the beam into a variety of pieces, where each discontinuity serves as the boundary between different zones of integration. But anyway, let us look at an example. So, example, I am given a beam, we have a cantilevered beam. Let's see, with a single point load on the end, so we'll keep things kind of simple. But you know what, just for fun, I'm going to put an upward point load on it, which is really odd. We're used to a cantilevered beam, you're used to seeing an upward, or you're used to seeing a downward point load, but you know what, just to mix things up, I will apply an upward point load. Now, let's see here. Now, I don't have I'm not going to provide you the EI, and that's okay, those are just constants. I'm going to do all this in terms of just EI. So that won't make it too difficult, but I will provide the other things that we'll need, like the dimensions and that kind of stuff. So we have point A on the left, and point B on the right. Our coordinate system is going to be fairly obvious and simple. If I can select the right color. It's just going to be x increasing to the right with 0 at point A. We have a cantilevered beam. And the overall length of this thing is going to be simple, it's going to be nice. A nice and simple, happy 10-foot long beam. So we basically have we have an immovable object here, a rigid support. We have a 10-foot long beam of some material and some cross-section jammed into this support, and then we've applied a 50 kip upward load directly to that. then I'm sure we could imagine some. I'm trying to think of what scenario might result in this, but it's hard to even say. Where would this actually happen? You know what? If I was actually to guess what this might be, if I were to try to actually interpret this as something real, maybe this would actually. I would actually be more inclined to think of a 50 kip lateral load than a 50 kip upward load. So what if we were looking at this in plan view, and this is actually coming from the side? But anyway, it doesn't matter. The diagrams are the same. Let's just say we have a 50 kip upward load, just for fun. So the first step is to find the reactions. So solution. Oh, I probably should tell you what we want to find. Solution. Well, the solution is 2.8 molar H2SO4. No, that's not what we're doing. This is mechanics of materials, not chemistry class. Develop. Let's say we want to get y as a function of x and theta as a function of x. So we're given this nonsense, and I want to develop y as a function of x and theta as a function of x. So let's do that thing I said. The first step is to find the reactions. Now, I have time today, so you know what, let me just go ahead and actually do that just for fun. Because why not? Let's be sticklers about it and do it nice and proper. Sum of moments about point A is equal to 0. We'll give you some stuff. Sum of forces in the y direction is equal to 0. We'll give us some stuff. And sum of forces in the x direction is equal to 0. We'll give us some interesting things. So let's work through each of these. Again, if you do not know how to do this, oh boy. Negative and, oh, let me actually draw these on the diagram, show them what these are. Again, we have MA. Actually, you know what? I'll just go ahead and draw the directions they have to be. I know this is going to have to be in this direction. And AY and AX, which we can just say is going to be equal to 0. AX. So let's find all this wonderful nonsense. Negative MA. And the reason I did this is because I know if this thing is generating moment that is clockwise, the resisting moment must be counterclockwise. Plus 10 feet times 50 kips equals 0. And this leads us to the reaction moment, MA, is equal to 500 kip feet clockwise. And then some forces in the vertical direction. Negative AY, and the reason I set this up as negative was if this is going up, this is obviously going to go down, etc., etc. Plus 50 kips is equal to 0, and this leads us inexorably to AY is 50 kips downward. And then, well, we obviously don't have any horizontal loads on this, so AX is simply equal to 0. This is child's play. You know how to do this by now. Okay, so next I want to get the shear and moment diagrams, and from these we will be able to get the shear and moment functions very easily. So 2 shear and moment diagrams. Diagrams. Language is fun. So the shear and moment diagrams here. Well, let me just show this here. So this is basically by inspection. So what's going to happen, we have a downward load, a downward vertical load, and then we have no other load until the end. So this is just going to go down, be horizontal, and then come back up. So V in kips, or yeah, V in kips, is just going to be like this. just going to be a constant negative shear all the way across the beam. So this is negative shear, and we'd have arrows like that. And to balance it, like this here. Then for the moment, I'm going to have, actually let me just go ahead and say, and we do know this is 10 feet long, and I should complete the diagram by saying this is negative 50 kips. So then, v as a function of x is simply negative 50 kips. It is a constant across the length of the beam, or along the length of the beam is probably better language. Then from this I can get the moment diagram. Well, this beam is going to be, well actually let me go back and say, okay, we have a reaction moment on the left side, and this is a clockwise moment, and we remember from when we learned about moment diagrams that this will cause an upward jump in the moment diagram. So this is going to immediately jump up 500. Now, this is negative, and the value of the shear here is negative 50 kips. The length of the beam is 10 feet, so the total area here is negative 500. So that means between the left end and the right end, this shear is the moment produced by this shear is going to cause a drop of 500. So we know we're going to be down here at 0 at the end, which makes sense. The free end of the beam, at free end of the beam, the shear and moment both should, well, not necessarily the shear, except when we get to the, I should say, at the end of the beam, after any, at the end of the beam, after any loads are applied, both the shear and moment should be 0. Now, this is a constant value relationship. This is a constant value relationship, which means that the integral is going to be linear, or that this function is going to be linear. So we just simply have a linear relationship, and this whole thing is going to be under positive bending. So this is m kip feet. And then I can say, we could get this by integration and solving for constants, or we could just say, hey look, this is clearly a linear equation. M as a function of x equals 500 minus 5x. I know how to find the equation between 2 points. Boom, boom, we're done. Yes, minus 50x. I apparently don't know how to do that. Minus 50x. Just like, I can find linear equations. Then I get it wrong. When you're giving a lecture, you gotta be very careful with statements of pride like that, because it's almost inevitable you're gonna screw something up right as you do that. I'm pretty sure that's a like constant of the universe. Just fate conspires to. Yeah, there should be like a corollary to Moore's law, like not Moore's law. What is that? Yeah, not Moore's law. Murphy's law. Yeah, there should be a corollary to Murphy's law that's like Murphy's law squared or something. You're really likely to screw something up when you tell somebody it's really easy. It's really when it's. Yeah, when you tell somebody something cannot go wrong, right then is the time that it is most likely to go wrong. So, anyway, it's why the Titanic sunk. They said it was unsinkable, and they just tempted fate, and there you are. And no, we can actually look at the Titanic from the point of view of engineering and analyze it from there, so please do not quote me as saying, oh, Professor Larson said that the Titanic sunk literally due to hubris and the fates. But anyway. Okay, let us develop the hubris function of the equation of the beam. Okay, so, well, we could get it that way, or we could actually say, let me show you how you would get it without doing just with the linear equation. Let me show you the integral way one more time. V as a function of x, we just know, is the integral of, let me show you how you would do, actually let me go back and say, what if I wanted to do this without just doing it by inspection? What if I actually wanted to do this via integral relationships? And that might be useful, because on this simple example it's not too bad, but for more complicated ones it might be an issue. So we're going to take the negative integral of w of x, but w of x is simply 0 here. Negative 0 dx. So then this is then just equal to 0 plus c1 and we'll need a boundary condition. Boundary condition, well, we need a known constraint slash value at a known x, value at a known x, at a known location x, and I do have a boundary condition that I know for shear. So again, even though we already sort of have the shear function, I just want to go through the process of finding it if we had a more complicated loading. The boundary condition is going to be the shear at x equals 0, in this case, is going to be equal to negative 50 kips. And then v as a function of x is equal to negative 50 kips. So we plug this in, we find that C1 is going to be negative 50, so again this leads us to C1 equals negative 50 here. So V of x is negative 50 kips. Then I can say my moment relationship with shear again is m as a function of x is equal to the integral of V of x dx, and we can just take the integral of this. Negative 50 dx is equal to negative 50x plus c2. Now I have some boundary conditions, and I actually have two I could use. I could say basically just depending on which one we feel is more convenient. We could say that m at x equals 0 is 500 kip feet. Again, just based on a reaction moment, but you gotta reverse it. Again, if we have a reaction of a clockwise reaction, it's going to cause the moment to jump up 500 at the left end there. Or we could also say, or m at x equals 10 feet is equal to 0. And so what if let me actually go through and show how that would work for both of these. So I could say m at x equals 0 equals negative 50 O times 0 plus C2 equals 500, and then C2 is simply equal to 500 kip feet. Or I could say m at x equals, or m at x equals 10 feet is equal to negative 50 times 10 feet plus C2 equals 0, or sorry, equals, equals 0, sorry. And from this C2, I would get that C2 is also equal to 500 kip feet. But regardless, I end up with m as a function of x is equal to negative 50x plus 500. And that's where that comes from, if we don't feel like doing it via inspection from the moment diagram. Now, our next step will be to develop the theta as a function of x. We're looking for the slope of the beam as a function of x. So we've done the hard work, the rest is just math. For develop theta as a function of x, and I am going to use the equation that we developed in the previous lesson, and that is going to be theta as a function of x equals the integral of m of x over ei dx is equal to 1 over ei times, let's say negative 50x plus 500 dx, or, I lost my integral sign, there we go, integral of negative 50x plus 500, or is simply equal to 1 over EI times negative 25 x squared plus 500x plus C3. So yay, we get another constant of integration. So we need a boundary condition. And what might that boundary condition be? Well, I do know one. Boundary condition. Consider this. Theta at x equals 0 is 0. This is a fixed support. So in other words, if I have a fixed support, what happens at a fixed support is that you can have a beam. But if I think of the shape of a deflected beam, this is the original, nice and horizontal, but then it's going to bend up like that if there's a load applied here, right? However, so the slope of this will be continuously varying along the beam. However, right at the support, right at the fixed support, we're going to have a slope of 0. So then if we apply this, theta at x equals 0 is equal to 1 over EI of negative 25 times 0 squared plus 500 times 0 plus C3. And this leads us to C3 is equal to 0. So in other words, theta as a function of x is equal to 1 over EI times negative 25 x squared plus 500x. And that is the full theta of x function. And next, my last step will be to find my actual deflection equation, which again is just math. Actually, let me see something. Oh well. 5, develop y as a function of x, or the deflection as a function of x. And I'm going to use the equation y as a function of x is equal to the integral of theta of x dx, or this is equal to then 1 over EI, just plugging in my theta of x equation I got previously, times the integral of negative 25 x squared plus 500x dx equals 1 over EI times negative 25 x to the third over 3 plus 250 x squared plus C4. And I know that at a fixed support, not only is the slope equal to 0, but the deflection is going to be equal to 0. Boundary condition: y at x equals 0 is equal to 0. And I can just substitute this in, and I will get 0 equals 1 over EI times negative 25 over 3 times 0 to the third plus 250 times 0 squared plus C4. And this leads us actually to that C4 is equal to 0. Or simply, y as a function of x is equal to 1 over EI times negative 25 over 3, negative 25 over 3 x cubed plus 250x squared, or 250x squared. And that is our final deflection equation. So we've got all the equations we need. Now I would like to provide a note. The boundary conditions are critical. See, notice here we had a nice fixed support, so we could say, oh, the rotation or the curvature, the slope at x equals 0 is 0. But what if I had something like a simply supported beam? Then it gets more complicated. And what you're going to need to do is, and I believe we'll maybe work through some of this in the next class, but the issue here is that if you have a beam that is deflecting like this, then you don't know the slope at either end. So what you would actually do is you would know two other things. You would know that the deflection at this end is 0 and the deflection at this end is 0. So you would run through the equation, the whole integration with and you'd end up with a y as a function of x with both a C3 and a C4. And you would use those two known positions to find the C3 and the C4. So that's the method for that. And then a couple other things. Let me show how to apply this. Find displacement at the end. In other words, how far is this thing actually bending? X equals 10 feet. Well, it's going to end up just as in terms of E and I, but that's okay. It's going to be y at x equals 10 feet is equal to 1 over EI times, that looks like a summation sign, negative 25 over 3 times 10 to the third plus 250 times 10 squared. And this then comes to 16,667 over EI. And so that's what the deflection is at x equals 10 feet. And the units would be, kip feet cubed. Well, actually, we need to multiply by kip feet cubed to make this equation valid. But the end result will actually be in inches, and it would be upward. Now, a few comments on this stuff. Let me just give you a few notes on this. Comments. So theta and x, theta is a function of x, and y is a function of x. Construction. Very similar. Cannot write today. To v of x, m of x. So if you have you need to divide it into a series of discontinuities, etc., etc. You will need boundary conditions. Watch your units. You can do everything in kips, or you can do everything in pounds, you can do everything in inches, or you can do everything in feet, but you don't want to mix up inches and feet. This is very easy to screw up. Watch your units. And again, watch for discontinuities. Abrupt changes in load or support. Either one represents a discontinuity. Alright, I think that'll do it for today. If you have any questions, feel free to email me. Again, for students taking the class this semester, the final exam is going to be on Friday. So it'll be from Friday from 6 p.m. to 9 p.m. and I think that'll do it for today. If you have any questions, feel free to email me, and as always, thank you.